Hello, we will discuss how we can use tubular system as a structural system for high-rise buildings. And one of them that we need to take a look at today is tube structure or tubular structure. This is tube, and tube is a four-sided structural member that can resist compressions and tensions. If you have a loadings in here, then this face will be subjected to tensions, and this face will receive a compressions. So if you draw the stress diagrams, something like this, tension and compression, and we see this tension compression coupled in many locations, many places of structural elements. For example, we have a beam here, and if you push it down, what happened? We have a compression with respect to the neutral. Okay, let's see, we have a beam like this, and if you push it down, we will have a compression above of the neutral axis, and we will have tensions below the neutral axis if the beam is simply supported in both ends here. And we have a CT couple in beams, and we learned that maybe mechanics of structural course. And same thing, if you put cantilevers like this, and vertical cantilevers, and you applied a lateral load as shown here, what we'll see this is a neutral axis, and this part we'll see tension, and this part we'll see compressions, tension, compressions. It's similar to this. You have cantilever and you push right here, then you have diffractions like this. Therefore, you have a tensions here and you have compressions here. So if you just take a look at this, and this is really similar to this behavior. So vertical cantilever structures, as you see over there, has the behavior similar to this, and we have tension, compression. But in order for this tube to be used as a building frame, you need probably a lot of windows. So you need a lot of windows like this. You need a lot of openings for window. So we need a little bit different from 100% tubular structure, but the behavior of this perforated tube is really similar to the one we have closed tubes, as you see over there. So that perforated tubular behavior will be very similar to this one. Okay, so this what we will be studying today, and how we can use this tubular structure with a lot of openings, and how we analyze the loading path from tension side to compression side. And again here, with respect to the neutral axis, we have a tension side here and compression side over there if your wind is acting this way. Okay. Okay, this is what we see as a typical tubular structures, and we have a all column. Column should be spaced very closely in order to maintain the benefits of the tubular structures. And we need a very thick, stiff spandrel girders and spandrel beams. Spandrel beams is the beam that connects the columns. closely here. And if you put lateral load right there, then you're going to have a tension side here, and at this side will be subjected to compression forces. Okay, now let's take a look at this. And you have here columns here. This is column. Each of this is column. Say this is column and this is column. Okay, this is column, this is column, or columns. And in between columns, we have a spandrel girders, right? So that we have a columns and spandrel girders, and we have columns and we have spandrel girders. And this is what we typically see from tubular structures. And this is columns, and this is spandrel girders, and with a very high stiffness here. All right, so this probably spacing between columns should be 3 to 5 meters, which is very close. And the spandrel girders should be stiff enough to transfer. Okay, let's take a look at one more columns with spandrel beams here. It's spandrel beams. And we have symmetric, right? So we have, if your loadings is hitting from this side, what happened? So we have a 1, 2, 3, 4, 5, 6 columns, and you will have a neutral axis right there, right? Neutral axis right there. And this side, all this side will be subjected to tension force. So if you plot the stress diagrams or force diagrams, you have tension here. This side, all tension, right? This side, what do we have? This side, all compressions, right? And this is all we know from previous classes of material mechanics and whatever. So these columns are subjected to tensions, right? Tension. And these columns are subjected to compressions. Right? Okay. Something like you see here, tension, compression, something like you see here, tension, compressions. And you are looking at from this side, right? You're looking at from this side, okay? Then you'll see tension on the left, compression on the right, and this is what you see. Okay, what happens here then? What does this spandrel girders do for you? These spandrel girders will carry shear force. And why shear force is very simple to understand. And the load here at the extreme side, you have the biggest tensions, and then your tension decreases. Tension decreases. This, according to this stress profile, and the magnitude of tension force depends on how far you from the neutral axis. We can say this as a strain compatibility, very similar to the theory called strain compatibility. Okay, strain is comparable. Strain increases linear fashion. Strain increases linearly from the neutral axis with respect to the distances from the neutral axis. And this is called a strain compatibility. And same thing, we can calculate the magnitude of the force, tension force can be also calculated based on the distances from the neutral axis. So you're having a largest force where you have a smallest force, cause your distance from here is smallest, whereas distance from here to here is largest. Okay, so this is proportional compared to the strengths, and also same strength compatibility theory can be applied here to calculate the magnitude of the force in tension side, and same thing for compression side, right? So we have here, say, compression also largest at farthest columns and reduces, and we have smallest compressions because we have shortest distance from the neutral axis and largest length from neutral axis, and the proportionality is again similar to that we see with the strength compatibilities. Right? So here, this is another force compatibility, if you will. Right? So this is a profile or distribution of tension and compression forces with respect to the neutral axis. Okay, this is what we see. And the problem is, if your spandrel gutter, just gutter, if your gutter must be stiff enough to form these force distributions. What I mean by is that if your beam or gutter or spandrel gutter is not stiff enough, so it produces a shear deformation like this, and same thing here, shear deformation like this, and shear deformation like this. Then what happens is that you don't see this distribution, because once your tension force at extreme column cannot be transferred, the column one next to it, right? The column next to it right here, if your gutter is not stiff enough so that it deforms, then this tension force cannot be transferred here. Cannot be transferred. So this ratio is not linearly decreasing anymore. So you're supposed to decrease your force according to the compatibility, depending on the distance from the neutral axis right here. But this ratio is not linear anymore. It's going to be like nonlinear, which indicates that your tension force rapidly decrease, fail to follow linear fashion. Why? Again, due to the stiffness which is not sufficient to transfer the shear forces. Look at here. This column tension and this column tensions are nothing more than a shearing force for gutter. Do you understand? So this tension force is becoming as a shear at gutter. And these shear forces must be resisted well to transfer to the next tension force on next columns, as you see over there, in linear fashion. Okay? When you have a perfect 100% shear capacity for beams, then you will notice these tensile forces are transformed linearly, and that's based on strength compatibility. So transferring mechanism will be obtained when your shear strength of a gutter is perfect, right? But in most cases, your shear strength cannot be perfect, so you must have some deformation in shear like this. Then what happens? Your shear cannot be transferred from here to here perfectly, 100%. There's some shear force is lost due to the shear deformations. Okay, shear forces from here to here is lost due to shear deformation. Okay, so what happens is your tensile forces on column reduces rapidly. Okay, and your linear transform mechanism is lost. We have some big tensile force here, and we have small tensile force here. Okay, so the only reason why you don't have a linear decrease based on compatibility is because your beam, spandular girder, spandular beam, cannot transfer shear forces well, because your shear strength is not enough for the building to transfer this force to this force, right? So again, what is this force and this force for girder? Shear force, right? So now shear is going up here, and this shear cannot go up. Why? Because your shear deformations occurs here, right? Instead of transferring shear force from here to here, your shear deformation occurs, so that the amount of shear forces that picked up at this location reduce, so that your tensile force on column next to this is reduced and reduced. And same thing. A few minutes ago, this is a neutral axis. We have a column, 1, 2, 3 columns. We had 3 columns, 1, 2, 3 columns. So I'm trying to draw it again. And if you see the 100% stiff shear deformations, then you go like this, right? Straight line. As you see over there, straight line, right? Straight line. And if you miss a little bit of the shear deformation and shear stiffness in order to transfer the actual load, then you have a shear deformation here, right? Like this. Yeah, shear deformation like this. Shear deformation like this. You know what happened? That you will have a, see, lag, shear lag in the structure, so that your vertical tension force can only be transferred with this height here, with this height here, with this height here. So we call this phenomenon as shear lag phenomenon. Okay, lag phenomenon. So, and if you see in here, your dotted line is a perfect column load transferring mechanism, whereas you have a little less here, something like this here. So your shear stiffness is not enough for you to transfer the vertical load based on linear trend here, right? So you lost this much, right? And this is because of the shear lag phenomena. Okay, now do you understand? So in this case, your structure is not behaving efficiently. The reason is that then your loading mostly supported by this column that is located at extreme parameters. For example, your columns here. So let's take a look at our frame. We have 1, 2, 3, 4, 5, 6. Right? We have this frame, and the neutral axis here in the middle. Right? So in this end, we have column as well here. 1, 2, 3, 4, 5, 6 here. So what happened here? when you have loading with the spandrel beam which is not stiff enough, then what happened here? We have a shear lag phenomenon, so that the tension force acting on this column cannot be transferred efficiently to the column next year, So I would say this and this will receive a little less tension forces. So the columns here will fully support the tension forces, but the column next here is not be able to be participating load resisting mechanism efficiently. So you're losing a efficient design of the building when your girder right here is not stiff enough as far as shear stiffness is concerned. Do you follow me? So that this building is inefficiently designed, and you need some revision on this design.